Welcome to this video where we want to demonstrate the use of STEMRE, which is a package that we have developed at STEM Research for use in mathematical computations, analysis, numerical simulation, and data fitting in the Python programming language. So the package name is STEMRE, and it can be found on the main pi.org website, as you can see here. Press the enter key to open the page. An easier way is simply to search for the package here. Just type its name here, STEMRE, with that spelling. Then hit the enter key to search for it. So this is the package name. This is the version and a short description of what it does. Just click on the link. It takes you to this home page of the package with some general information about this package. So this is a package name, as you have said. This is the version. This is the installation statement. And then here we have general information about the package first. We get the package name as STEMRE, then what the package does. Then we have the installation syntax or command. We install this package using the pip install command, just as you will install any other package, then specifying the package name with the correct spelling. And then after successfully installing the package, before it can be used in any Python session, you must start by importing it using the import statement. Of course, you can also import it using different methods as available in Python. We prefer this way here. Then below it, we give some 4 examples on how to use some functions in the package. And we believe that by giving these 4 examples here, then any user should be fine to get started with this package that we have developed at STEM Research. In the first example, we give a function that is used to to differentiate parametric equations. Here you can see these are the 2 equations, which are functions of t that we want to integrate parametrically to order n is equals to 3. Then in the next example, we use the Richardson extrapolation methods to find the numerical derivative of a given function for this function here, particularly then when the value of x is equals to 2.5. The third example is Gauss Legendre quadrature integration, which is a numerical technique for finding the integral of a given mathematical expression for given integral limits, then with a specified number of intervals using the Gauss-Legendre function of the STEMRE package. Then lastly, we look at initial value problems, where in particular we are going to use the 4th order Runge-Kutta method to numerically integrate this ODE here for the time span between 0 and 1, starting with an initial value of y is equals to 3 and going with a step size of 0.12. So we will be looking at these 4 examples in this video demonstration. As we said, the first thing is to install the package. So to install this package here, just click this icon, then open your Anaconda prompt like that. Sorry, let me share the screen. Screen share. So this is how the Anaconda prompt looks like. So just type the syntax there, pip install STEMRE, then hit the enter key. So that should begin installing that package, and it has successfully installed it. So now once the installation is successful, we can carry on with what we like to do. So you as a user are free to use any IDE, Python IDE to run your syntax. But for our case, we are going to use the Jupyter notebooks to do that. So just open your Jupyter notebook. This is the home page of that, the Jupyter notebooks. Then I want us to open a new notebook, which is done by simply clicking on this icon here, the new icon, click on it. Then from this short drop-down menu that pops up, you click Python 3. This will open a new notebook, as you can see here, with the first cell created and activated, where now you can begin to type your inputs. For those who are new to Python, rather to Jupyter notebooks, I can just demonstrate two things on how to run Jupyter cells. This is known as a cell. So once you type your syntax here, there are a couple of ways of running the syntax. The first one I will want us to look at is simply click this run icon at the top here. So if I click on it, well, there's no syntax here, so it will have run whatever is here, then moves on to the next cell. Another way to run syntax is simply hit the shift key on your keyboard and press the enter key. So you are pressing the shift and enter key simultaneously. Again, that will run the cell and create a new cell, as you can see. Then the next way is to hit the control and enter key simultaneously, like that. Now doing that will run the cell, but will not create a new cell. It's in the first case where we say the shift plus enter runs the contents of that cell and creates a new cell, as you can see. But control and enter only runs the contents of that cell, but does not create a new cell. So for me, I always prefer to use the shift plus enter key to both run the cell and create a new empty cell for new syntax. To delete all those cells, just highlight all of them using, well, just click your mouse in the first cell, hold down the shift key, then click the last cell to the far right. That will select all those cells. Then from the menu here, click on edit and delete cells. So this is where we want to begin. So as we said, we'll be using the examples that we have provided on this page here. So the first one, as we said, you must start by importing the package using that import statement. Do that, copy and paste it here. Then hit the shift enter key. So it has already run. A way to know that your package has run is when this changes from a star to a numerical value. So unless usually when the syntax is running, rather when the Python interpreter is still running the code that you have entered in a particular cell, then it will always indicate that by putting here a star. But now when the star changes to a numerical value, then it means that that statement has worked successfully. Otherwise, Python will generate an error. So in our case, the import statement has worked correctly. So we move on to see how we can use our examples, where the first example was to differentiate two expressions parametrically. So we are looking at these expressions here, which, as we said, and as you can see, they are functions of t. And we're doing that integration to order n is equals to 3. So just copy that syntax and paste it in a new Jupyter notebook cell. Then you press shift plus enter key to run it. So that's the result that you find. This is the value, rather the third order derivative when these two expressions are differentiated parametrically. So that is all for that first example. Then in the next example, we are using the Richardson extrapolation to find the value of the numerical derivative of this function when x is equals to 2.5. So again, just copy the whole of that syntax go to your Jupyter notebook and paste it in any cell. As a preference, I want to have these import statements in the very first cell. That's just a preference, it's not a requirement. When you are working with the Jupyter, you can put those statements anywhere in any cell. So hit Shift Enter key to run the new, to rerun this cell here. If you don't rerun it, then we will not have this package in our workspace. So that is it. So as we said, our aim is to find the first derivative of this function here when x is equals to 2.5 numerically. We are doing this numerically. So it means that this is what the answer we get would be an approximate to the exact value. So with that, simply hit Shift and Enter key simultaneously, and you get these results. Allow me to add another statement here, which is known as, so I needed to import this package here, prefer to have it here. So allow me to add sim init printing this will just allow these results to be typed in, well, some larger font, rather in latex format. So run that cell, then run this cell. So that's what you get, this is the result you get. So as we say, this is an approximate value which is found by numerically integrating this function here and then finding its value when x is equals to 2.5. So I want us to find the exact value of this, the first derivative of this function here, then find its value when x is equals to 2.5, then compare the two values. So in that case, I just say d is equals to, I use the SymPy package, particularly the function diff, which performs differentiation, then copy that expression, paste it here. Then I must remember to change this from np to sim. So now we are calling, in the first case, we were calling this function, the exponent function, from the numpy package. But this time, because we are doing symbolic integration, differentiation, then we'll be using the SymPy package. So in that case, we must call it from the SymPy package. Then you define your independent variable. So in this case, it is x. Well, in this case, it's optional, given that this function here is a univariate function. So you can either put the x here or just leave it out. But in our case, I just prefer to put it anyway, even though it's optional. Then, so this one here finds the first derivative of that given function. Now the next step, as we said, is now we want to find the value of that first derivative when x is equals to 2.5. So we do that by using the subs function, and you specify x and specify its value 2.5, as you can see here. Then hit just display the results by entering the object name d. So now run the contents of that cell by hitting Shift and Enter key. There is a mistake we have made. Can calculate derivative with respect to 2.5. So what is telling us that here is 2.5, and you can see that actually that's true, because we, in the workspace, we have x defined as 2.5. So that's where the error is coming from. Now, to correct that error, I must first declare x as a symbolic variable. So I do that by simply saying symbols, then x, like that. Now you can run the contents of that cell to get the exact answer. So now you can compare the two answers, this one here and this one here, to get the exact error. To do that, I simply get the difference between the exact value and the approximated value. At the top here, we called the approximated value. This value here was stored in this object known as dx. So here we are just getting the difference between this value and this value here. So press the Shift and Enter key to get the error. So we can see that the error is 10 to power minus 9. So you can see that the approximated value, the numerical approximated value is quite close to the exact value using the Richardson extrapolation method. So that is it for that method. The next one is Legendre, Gauss-Legendre quadrature integration. Again, simply copy all of that syntax. I can exclude this line here because we know that we already have imported the NumPy package, so there is no need to import it again. Paste it in a new cell, and I would like us to store that in an object known as I1. Then we print it as follows. So in this case, as you have already mentioned, we are integrating this expression here numerically from x is equals to 0 to x is equals to 4. And we are using the Gauss-Legendre function from our package. So that is fine. You just run the syntax again by pressing Shift and the Enter key simultaneously. So you get this result. Now again, you can find the exact value of this derivative of this function here from 0 to 4. And again, you'll be using the SymPy package. Do that by saying sim.integrate that expression, just copy and paste it here. Then you say x from 0 to 4. Those are the integration limits as can be seen here. Then you remember to change this from NP to sim, which means that we now are calling this function here from the SymPy package and not the NumPy package. Then say I2 to print the results. So enter. That's the result that you get. Well, I can put it in numerical form by adding that function. And then rerun the syntax. So you can compare that you can look at this and see that these two values are almost the same. Again, we can just do that. We can get the difference to get the exact error. So I get the difference between the exact value, which we call I2, and the approximated value, which we call I1, and see what the exact error is. So the exact error is this value times 10 to the power of minus 15. It's actually very, very close to the approximated value. So again, that is it for that procedure, the Gauss-Legendre quadrature integration. Last, we'll look at the initial value problems where we said that we are going to use the fourth order Runge-Kutta method to integrate this ODE here numerically between these given time points 0 and 1, starting with an initial value of y is equals to 3 and moving in steps of 0.12. So again, copy the whole of that syntax and come and paste it in a new cell. Then run it by pressing the Shift and Enter key simultaneously. So this is the graph you get. Then down here you get a table for the results. This is the exact solution. Then this is the approximated solution. This is the difference between the exact and approximated solutions. So I can just describe maybe a few other things you can change in this code here to get different results. In our case, you can, well, we had h rather the step size defined as 0.12. Someone can have a different step size, for example, 0.2. That's how you define it. You just change from 0.1 to 0.2 or any other value that you are given. Then you press the Enter key. Oh, sorry, Shift plus Enter key, and you get that new graph and these new results. A different person will, instead of being given the step size, he or she would be given the value of n, rather the number of steps. And you do that by changing that h to n, then specifying the number of steps. Let's say we wanted 20 steps, then you hit the shift and enter key to run the syntax. So again, you get a different graph and a different table here with different values. Again, a different person. Let me change this to, for example, say 15. Then this time we are not using the fourth order Runge-Kutta method, but we are using the explicit Euler method of numerically integrating ODEs. So explicit Euler like that. Then you hit shift plus enter key. So you get that graph and this new table here. The function provides a way to customize this graph to some extent. You can change the graph title, you can change the y-axis and the x-axis, then you can change the plot lines and so on. So to do that, you allow me to use the help function, just say stm.ivps. That's a function that the function inside this temporary package that is used to numerically integrate ODEs. The function that we are using here, it's this function here. So I want to find help for that function. So I just do that, then run that cell. It gives me some helpful information. I'm interested in this statement here that customizes that graph. So copy, then paste it somewhere here. You can paste it anywhere within this function here. Ensure that it's correctly, the indentation is correct. You can break it in at that point, then change this. I can give it a new title name, say explicit Euler method. Then I can call it time, for example. I call it days, where that time is given in days. Then the axis, y-axis, I can just leave it, say it's y. Then now you press the shift and enter key to run the syntax. I've made a mistake somewhere. There are 2 commas here, so just remove one, then enter. So that's the graph that you get. Now, here we have 2 graphs. We have the graph, we have this function here, which is the ODE, and we have the exact value. Someone else may choose not to have this value here. So just set that to none and then hit the enter key. Then here you can, if someone increase this number of points, for example, to that 5, then this marker points here will disappear like that. You can just do that and hit shift enter. You see that you get a new graph, and this time the marker points are not there. The package is designed, this function here is designed in that manner so that in the case where n is too large, actually when n is greater than 30, then those markers points are not added to the graph. We just generate a straight line to avoid too many. Well, if those points are plotted, then they will be congested on this graph. So thank you for your time and for watching this video. That was a short video to introduce you to the package that we have developed at STEM Research. And as we said, it's used mainly for mathematical computations, numerical analysis, data fitting, and simulations in the Python library. So thank you once again.